All right, we're getting into chapter 12, Introduction to Sequences and Series. Sequences and Series. I really like this chapter because it's kind of about patterns, and I mean, sometimes patterns are kind of neat. I want to show you a few things actually that you might or may not have heard about that might pique your interest a little bit when we get into some of these specific types of patterns. So, let's just cut to the chase. There's some words and stuff we'll talk about and things are happening. Well, let's get down to the start of it. Let's take a little, stroll down history lane for a minute. In the year 1202, I don't know how you would say that in that year, 1202, I don't know, 1202, back in '02, Italian mathematician Leonardo Fibonacci, or as they say, Leonardo Fibonacci, just ignore me, describes how fast rabbits breed under ideal circumstances. Interesting fact. That's it. That's the end of the video. I will see you guys in class next week. I'm just kidding. Fibonacci noted the number of pairs of rabbits each month and formed the famous pattern called the Fibonacci Sequence. Don't mind me. So a sequence is an ordered set of numbers. Each number in the sequence is a term of the sequence. A sequence may be infinite, that continues without end, such as the natural numbers, or a finite sequence that has a limited number of terms. So a sequence is just like a list of numbers, but it's typically a list of numbers that has some sort of pattern to it. So for example, I could make a sequence that goes 2, 4, I hate when it does that, 2, 4, 6, 8, 10, right, etc. Now this is a sequence. It's a list of numbers. Now, this one would be an infinite sequence if I said it's all the even numbers, because even numbers this list can go on forever. But if I say it's all the even numbers up to 10, well, then now I've made it a finite sequence. It's limited to only those numbers that are even and positive, I suppose, up to 10. So an infinite sequence can be something that goes forever, like all even numbers, or a finite sequence which has some sort of cap to it, right? All even numbers up to 10, for example. But a sequence is a sequence. It's basically a sequence of numbers, a list of numbers, typically with some sort of arrangement to them. Now, the reason why I talk about Fibonacci is because he discovered something called the Fibonacci sequence. So before we get into all of this, I know it's later on in the slides and stuff, but I kind of want to show you now. If you go to Google, a good old friend Google, and you type in Fibonacci sequence, right? You get some really geeky math things, okay? But also, if you go to images, look what pops up. Of course, you got more geeky math things. You got this weird looking spiral. That's a very popular thing, you'll notice. But if we scroll down, look, art. These things, Fibonacci sequence, or better known as the golden ratio, is seen all over the place when it comes to nature. For example, our Mr. Fibonacci guy discovered it in just simply the breeding of rabbits. Rabbits would breed apparently at this ratio, and they would grow at this ratio, which is known as the golden ratio, which derives from the Fibonacci sequence. And I'll talk a little bit more about what the Fibonacci sequence is, but I want to go ahead and show you, because it's very interesting, some of the things you see out in the world that have this sort of ratio to them. Now, the spiral is obviously very common. I like the sunflower. If you look down, the sunflower, I think that's pretty cool as well. Galaxies. I don't know if there's a galaxy picture in here. Oh, there's Trump's hair, because why not? That's clean and fresh. But a galaxy, you know how there's like a hurricane. You can see a hurricane there. They all have this ratio. Now, as far as sunflowers go, while it's here, and also I believe this applies to pine cones as well. If you look at the sunflower and you look at the spiraling towards the left, right, versus towards the right. I don't know if I can illustrate this for you. I'm just trying to, again, pique your interest here. So if you look at the spirals that go toward the left, like this, versus the spirals that go towards the right, the comparison between how many times you end up going left versus going right, I believe this is the case, is given by that golden ratio, which is also kind of cool. I could be wrong there. I'm not going to count them, but I believe that's what I remember it saying. But it is the golden ratio. Oh, I got to click the X. I was really confused. But the golden ratio is a really, really interesting concept. It applies to a lot of things. It's not just shapes, although most of these images seem to show shapes. It applies to a lot of things as well. You got galaxy, you got tree, Pascal's triangle, human. So this is an art thing. Yeah. The ratio even of our bodies is really interesting. The golden ratio, how that works. I'm not going to scroll through this too much. Who knows what I'm going to run into. But let's go back to the math. Okay. But I just wanted to tell you that it's Google the golden ratio and see what you find, because it's in music, it's in art, it's in everything, and it's mathematical minded. And this guy Fibonacci, kind of the sorcerer of it all. So this all is good. This is kind of notation, so I think you'll see this on the next slide. Well, you kind of sort of see it. But when I write a sub n, this is going to refer to the nth term of the sequence. So if I write a sub 1, then I'm referring to the first term in the sequence. A sub 2, I'm referring to the second term in the sequence. A sub 25, the 25th term in the sequence. So if you were to look at, our even number sequence, 2, 4, 6, 8, 10, etc. 2 would be, A1 because it's the first term, 4 would be A2, and I'm guessing 50, if this all went all the way to 50, 50 would be the 25th term of the sequence, which would be A25. And when I say A sub n, I just refer to any number in that sequence. The nth term could be the third, the fourth, the fifth. I'm just referring to a term in general, if that makes sense. So recursive formula. Yes. I'm trying to read this as I go to sort of emphasize any key ideas. Now, this talks about the Fibonacci sequence. So the Fibonacci sequence, what it is you start with 1. Because you have to start with 1. That's if you start with 0. Basically, it's taking the previous two numbers, adding them together to get the third number. So 1 plus 1 is 2. And then you take these two numbers, add them together to get the next term in the sequence. 1 plus 2 is 3. Right? Then you take those two numbers, you add them together to get the next term in the sequence. 2 plus 3 is 5. And again, you take those to get the next term in the sequence, which would be 8. Then you have 5 plus 8, which makes 13. And this is how the sequence is formed. So it's a pattern of numbers, and each successive number is based off of the addition of the previous two. And how we write that in terms of, recursively, I guess, is like this. A sub n, which means the nth term, is a sub n minus 2 plus a sub n minus 1. So what that means is, let's say you're talking about, the 7th term in the sequence. Well, that would be the a sub 7 minus 2, which 7 minus 2 would be 5. So that would mean it's the 5th term in the sequence plus the, again, if n is 7, then it'd be 7 minus 1, which would be 6. So the 7th term is the 5th term plus the 6th term, or essentially, another way you can read this is the nth term is the sum of the number 2 terms before it and the number right before it. So the previous two numbers added together make the next number. It's sort of another way of reading that. So it's kind of the formula because, yeah. A sub n. So like I said earlier, when you see A sub n, that's how you say it. I might just say an. I don't know, or a1 or a2 instead of a sub 1, a sub 2, just to not like choke on my words. All right. So now we're going to kind of fill out a sequence given the recursive formula for that sequence. So the recursive formula is just telling us what the pattern is, and we're going to write the sequence based on the pattern that it tells us to get. So this tells me that my first term is -2. So let me write my sequence down here. So we're going to start with -2. And then the next term of the sequence, so the the A2 term, right? So I'm going to say n is 2 for the second term of the sequence, would be 3 times A 2 minus 1. Now, 2 minus 1 is 1, right? So that's going to mean that it's the previous term. The A1 term plus 2. So 3 times the A plus 1, or A1 term plus 2. So we already know the A1 term is -2, so this is really 3 times -2 plus 2. So the second term in the sequence is -6 plus 2, which is -4. So there's your second term in the sequence. So that's A2. This is A1. This is A2. If you wanted to find the third term in the sequence, then you would have n be 3. And then if you had 3 minus 1, 3 minus 1 would be 2. So you're going to take the A2 term, plug that in. So the A2 term was -4. So you have 3 times -4 plus 2. That's -12 plus 2, which makes -10. So -10 is the A3 term. And we're going to do this for 5 terms. We're going to find the first 5. So the A4 term is going to be the 4 minus 1, right? 4 minus 1 is 3, so it's going to be the 3 times the third term plus 2. The third term was -10. So basically, it's 3 times the previous term plus 2. That's going to be -30 plus 2, which is -28. And then we got one more to do. So the fifth term is going to be 3 times the fourth term plus 2. And the fourth term was -28. Oh God, what's 3 times -28? If you hear my chair squeaking, that's just, I'm sorry. 28 times 3 is -84 plus 2 would be -82. So there's your first 5 terms of this sequence. Right? Yes, got it right. Killing it. All right. So here's another example. It tells us the first term is -5. It's already filled in. Obviously, this is using a table outlay, so that's cool. So the nth term is the n minus 1. So this just really means the previous term, because if you're looking at, like, let's say the second term, right, then it'd be 2 minus 1. 2 minus 1 is 1. So that would just mean the first term in the sequence, so just the previous term, minus 8. So if we're talking about the second term, a sub 2 minus 1 is a sub 1, which you already know a sub 1 is -5. So it's -5 minus 8, which makes -13 as your A2 value. And so now your A3 value will take your A2 value minus 8. So that'll be -13 minus 8, which makes -21. All right. And then the A sub 4 value will take the A sub 3 value minus 8. So that's going to be the -21 minus 8, which makes -29. And then your A sub 5 value would be your A sub 4th value minus 8. So the fifth term equals the fourth term minus 8. So the fourth term was -29. -29 minus 8 is -37. Right? Yep. So there you go. Again, it's just telling you the formula. I think you just really got to get used to the reading the n stuff. So the first term is 2. It's given to us. Then the second term, if we want to find the second term, it'll be -3 times, again, if you plug 2 in here, it'd be 2 minus 1, which would mean the a sub 1 term, which is the first term, which we already know is 2. So it's going to be -3 times the first term, which was 2. That's -6. And then the third term in the sequence is going to be -3 times the second term of the sequence. So that'll be -3 times -6, which is +18. And the fourth term in the sequence will be -3 times the previous term, the third term in the sequence, which was 18. So it'd be -3 times 18. Oh boy, I think you get the idea. I'm going to let the calculator do this because I can't necessarily, I'm not going to bother trying to think right now of what that is. -54. I knew that. And so on. So you can kind of see the pattern there. Okay, I was just kind of looking at this one because I was confused. It didn't really tell us what the first term was. So I guess we're assuming that the first term is, I guess not the first term, but that you would use n as 1. I guess that makes sense, yeah. So a sub n, so if you want to know what the first term is, right, a sub 1, then you got to plug it into the formula that's giving you. So 3 to the first power minus 1, which would be 3 minus 1, which is 2. So that's how they get 2. So that's how they get the first term. The second term of the sequence will be 3 to the second power minus 1, which makes 9 minus 1, which is 8. The third term of the sequence will be 3 to the third power minus 1, which is 27 minus 1, which makes 26. So you can see how they plugged it in there. So they didn't give us a first term. They just told you straight up, here's the formula. Plug in a number for the n, obviously 1 for the first term, 2 for the second term, 3 for the third term, and get the values for them. All right, same idea here. So if we want to know what the first term is, then we have to plug in n as 1. So because if we put n as 1, that's the first term. So we're going to use n as 1 in the formula. So it'd be 1 squared minus 2 times 1, which that's 1 minus 2. So that's -1 as a result. If we wanted the second term of the sequence, then n is going to be 2. So that's going to be 2 squared minus 2 times 2. And that's 4 minus 4, which is 0. If we wanted a third term of the sequence, then we're going to use n as 3. So it'll be 3 squared minus 2 times 3, which is 9 minus 6, which is 3. And you get the idea. Let's go ahead and put the other results up here. All right, I think I'll go ahead and show a few more of these. If there's anything new pop up, I'll do those, but I think you get the idea for those. All right, we'll probably talk about those in the next video. Yeah, I'll save these for another video. I don't want to make this too long, but there is a linear sequence, and there's also a geometric sequence. I don't know if that's on this PowerPoint or not. Yeah, exponential, geometric, kind of the same thing. So we'll talk about those things in the next video, but at least we have the beginning stages of what a sequence is down, and hopefully the whole A, N stuff doesn't confuse you too much. All right, I'll see you guys later. Bye.